After video 1, we found out that basically the natural log of x from infinity to 1 is going to be infinitely large. We call that a divergent value. That means we can't come to one specific area. It just keeps getting bigger and bigger and bigger forever because it is really wide. Okay? But we also know that's not the proper way of writing it. We would actually write, if we were doing this the proper way, the natural log of b minus the log of 1. But as the limit approaches infinity, oops, not b, sorry, that was the wrong problem. How about a? That's what it says right there. But it still comes up with the exact same value. In number 2, if I think about this in Mr. Hannon's unofficial way, I plug in the upper limit, then I plug in the lower limit of -1 or negative infinity. That's not exactly what we'll do for real, but that will give you an idea of what it looks like. This ends up being 1 minus, 1 divided by infinity, that's 0. This answer actually has an area of 1. It converges. If I want to do this correctly, I'm not going to put negative infinity there. I'm just going to write that b approaches negative infinity. That's really messy, but that's what I did. I just put the limit in here, but it's the same thing. So then we come to our third example. This is true for all of our functions here. There's no set way of knowing exactly which ones are going to converge or diverge for sure unless you take the integral and plug it in. We will learn something in our chapter on sequences and series, it's chapter 9, where it'll kind of let us know if you see the power here, that might indicate if it's going to converge or if it's going to diverge. And it turns out if it's a little bigger than 1 and in the denominator, it might just converge if it's going along the x-axis. If it's going up here, oh, it's so complicated. Don't use the shortcut, just take the integral. Okay, for the last one, how are we going to do this? It's very easy. And all it takes is a little kung fu. Oh, look, I split it in 2. I'm taking one integral of the left side and one of the right side because I have to stop right at 2. I can't plug 2 in. In fact, it's just flat out undefined if I plug 2 in. But what can I do? I can go from 0 to a, and I can also go from b to 4. So what do those values of a and b represent? It turns out that a is going to be just a little smaller than 2. It's going to approach 2 from the left. The second interval will be just past 2 all the way up to 4. So now we're looking at limits. When we have that vertical asymptote, we're going to split this up so that we have one section before, one section after, and we're going to use limits where we're not going to hit right at 2, but we're going to go right up next to it as close as possible. We're going to have a limit. So at this point, integrate. Then once we've integrated, plug in the numbers. Note that I've taken the upper limit minus the lower for this integral, and the upper limit minus the lower for that integral. And then finally do some basic algebra. When we look at those limit portions, we get something very close to 0 in the denominator, both here and over there. Notice the signs. This is a -1 and this is a negative number. Very close to 0. But what happens when you have any number divided by something close to 0? As I recall, that would be infinitely large, and 1 divided by 0 would be infinitely large. So apparently I have 2 infinity minus 1. I don't think the -1 does much. I'm going to take a moment and say that answer approaches infinity. It's an infinitely large area, and it diverges. It diverges. That's basically how you do improper integrals. Let's look at a few examples in the next video.